Okay, we're going to continue on. Last time we got into chapter 10, which is energy. And again, sort of the last chapter just going to be on our exam, which I think is coming up next week as well. So keep that in mind. Make sure you're doing the homework. Its date has now been readjusted one more time. So hopefully it will stay at the right date. It's due with obviously the rest of them on the 17th, I want to say, Sunday coming up, I think. So keep that in mind. So last time we talked about energy, and really, as we'll talk about today as well, we kind of talked about two main sort of energy processes, and those are exothermic, which means that heat and energy is released, and endothermic type processes, where heat and energy is absorbed. And we also talked about the idea of the law of conservation of energy, which is sort of the first law of thermodynamics. And the idea really we think about kind of two things when we think about energy sort of flow. We have the system, which is pretty much anything that you're dealing with. So it could be your beaker, your flask, test tube. And then pretty much everything, again, outside of that is going to be our surrounding. And when we think about energy sort of being gained and lost, we think of it as sort of a nice, perfect sort of exchange, which means if, for example, the system gives away a certain amount of energy, the surroundings should pick up pretty much the same amount of energy, and vice versa. If the surroundings sort of give away a certain amount of energy, the system should also pick it up. It is the same amount in the sense of sort of the numerical value. It should be the same amount, but it will be different in terms of the signs that we associate with exothermic and endothermic. Exothermic, typically energy values, as we also talked about, I think last time, are typically negative, while endothermic guys are typically positive sort of values. And what that means is the system can give away a certain amount of energy, which would be exothermic for the system. And if the surroundings picks up that energy, then it will be endothermic for the surroundings, and vice versa. The surroundings can sort of give away a certain amount of energy, which would be exothermic for the surroundings. And if that sort of system there picks up the energy, then it would be endothermic for the system. So sort of that exchange of energy that can happen, it can actually go in either direction. And again, it's usually the same amount of energy, just really the sign of those values are different to indicate which way it is sort of moving. Any questions on some of that stuff we talked about last time? All right, so to continue on, this is, I think, where we laid off. And the idea of thermodynamics, by the way, which the first law of thermodynamics, I'll spit that out, is the law of conservation of energy. So we deal a lot with sort of the energy aspect of thermodynamics in this class. And then in Chem 1A, you'll deal with it. And in Chem 1B, you'll deal with the rest of thermodynamics, which is like delta S, entropy, and delta G, which is Gibbs free energy and things like that. Now, a lot of times what thermodynamics really deals with is the idea of whether or not a reaction is sort of spontaneous. So more so when you get to 1B, you deal a lot with that about, whether or not that reaction is spontaneous. And sometimes people have, again, a sort of misconception about the word spontaneous and what it means in this sort of application. So when we say a reaction is spontaneous, it really has nothing to do with how fast or slow the reaction takes place. A lot of times people hear spontaneous, they think like snap your fingers is going to happen like really, really fast. And that's actually the area of study in chemistry, which is known as kinetics, where you study how fast or slow a reaction takes place. But thermodynamics means that if a reaction is sort of spontaneous, that reaction under those particular conditions will take place. It could be really fast, could be really slow, could be kind of in between. But it has really nothing to do necessarily with how fast or slow the reaction takes place, which, like I said, is more of a sort of kinetic sort of application of it. Now, things like energy, pressure, volume, and temperature, these are all what are referred to as state functions. And state functions, there's really only two things that are important in a state function, and that essentially is kind of where you start and where you finish, kind of your initial and final stages. And that's why when we look at things like energy, pressure, and volume, as we can see there to the right, we take like final minus initial, and that's really the important thing. So for example, we look at these two hikers here. They both started at the same location. They both really ended at the same location. The guy in the blue path here took the more direct route up the mountain. The guy in the red path took the more scenic route up into the mountain there. But they both ended up really in the same location. So in terms of their potential energy, where they started and where they ended is basically the same thing. Same positions for both of them. And that means that they do possess the same potential energy. Another important aspect is when people think about chemical reactions or equations, we oftentimes think of them as sort of happening in like a one-step sort of fashion. And a lot of reactions, that's not really the case. It's just like a one from the reactants to the products. So when we look at a reaction, we have reactants, which is our starting material, and they go to products, which is what is really formed. And when we look at a reaction, say like A plus B goes to E plus F. Now, sometimes people think that this is just like a one-step process. It could go that way, but it actually could occur in multiple individual steps. Like, for example, you could have A plus B goes to C plus D, and then maybe C plus D goes to E plus F. And maybe it actually happens in sort of a series of steps where each of these steps has a certain amount of energy associated with that process. And you could actually add equations together. And when we add equations together, pretty much anything that's on opposite sides of the arrow will essentially cancel each other out or reduce down. It's kind of like in math. You can think of the arrow like an equal sign, like you're subtracting it to the other side. And essentially, when we look at this example, C's on the left, C's on the right, so they will cancel. D's on the left and D's on the right, it will cancel. And we have A plus B goes to E plus F. And if there was a certain amount of energy required to do step one and step two, the amount of energy for this guy would be basically step one and step two basically together. And a lot of reactions happen maybe in a couple of steps, 3 steps, 4 steps. Another thing that you'll learn when you go to 1B is what's sometimes referred to as reaction mechanisms, and that's sort of the different sort of individual steps that occur. So when we take something like the change in energy, change in pressure, change in volume, and change in temperature, that's essentially doing our final state minus our initial state. When we look at a chemical reaction, really our products is our ending state, and our reactants is really where we start. So a very common sort of unit of energy that we'll talk a little bit about in this class, and you'll see again in 1A, that people use to sort of describe the energy associated with a reaction is what's referred to as delta H. And this is the change in enthalpy. And that's what the little delta symbol means, or the triangle. And it's basically like the heat of a reaction. And when we take the delta H for a reaction, we basically take the delta H values of the reactant, of the products. Try that again. Of our products minus the delta H value of our reactants. So our products minus the delta H value of our reactants. So when we do that, that's essentially like taking our final state, which is our products, minus the energy associated with our reactants, which is where we start with. And delta H, as we'll talk about, is an important factor, and it does follow the same sort of suit. If we end up with a delta H value that is negative, that's going to be an exothermic type process. And if we end up with a delta H value that's positive, that usually results in an endothermic type process along here. So a lot of what we look at in terms of energy and a lot of really thermodynamic sort of calculations involve taking products minus reactants, again, your final state minus your initial state, as they are state functions. And it doesn't really matter if it takes 4 reactions to get there, or 7 reactions, or 1 reaction. The only really two important steps along the way are where you start and where you end. Any questions on that there? So we talked maybe about some of these energy units, but let's officially talk about them here. And none of these, again, are negative. These are just from PowerPoint here. Right here. So the most common unit that we use for energy is joules. And this relationship that a joule is equal to 1 kilogram meter squared over second squared is something you should know. We probably won't come across it too much in this class, that relationship, or use it too much, but definitely in 1A and then 1B as well. You use it a lot in that sort of class. So when we talk about a joule, it equals 1 kilogram meter squared second squared. And definitely this relationship, joules and also kilojoules, are very common units of energy. I would say probably the two most common units of energy that you'll see in chemistry, which is joules and kilojoules. And it's the kilo sort of prefix there. So we have 1,000 joules is a kilojoule. You definitely should know that because we will use it a lot. Another unit that is sometimes used by chemists to express energy is calories with a little c. And the definition of a calorie is the amount of energy that's required to raise 1 gram of water by 1 degree Celsius. And there are two units that are also kind of used with calories. There are 1,000 little calories and 1 kilocalorie. So that is another sort of one that comes up. I will say probably not as often as joules and kilojoules being used, but when we talk about this particular chapter here with specific heat, calories does sort of pop in there occasionally along the way, and kilocalories like that. That means that we should have a conversion between the two, which once again, that definitely is used a lot. 1 calorie is 4.184 joules. That number, 4.184 joules, is used a lot in this energy chapter. So make sure you commit that to memory. It's also what is known as the specific heat of water, liquid water, that we'll talk about a little later on. There's also nutritional calories, which is a capital C. And 1 nutritional calorie is actually 1,000 of the little calories. And that is the same as 1 kilocalorie. So nutritional calories we come across occasionally is the unit they use for energy, like in food or when you exercise and stuff like that. And that is, again, 1,000 of our little calories there with the C, and 1 kilocalorie. Like when you look on the treadmill, they sometimes tell you how many kilocalories you burnt, and that's nutritional calories, which is 1,000 again of the kind of little guys. Any questions on any of that there? All right. Now, we might have touched upon it last time, but the idea of thermal energy and sort of temperature, when we talk about thermal energy, that is really the amount of energy associated with the random movement of atoms or molecules. And it is based on really how much atoms or molecules you have. So the greater the number of atoms or molecules, the more thermal energy that some sample will have. And there is a difference, again, between sort of thermal energy and temperature. We oftentimes use temperature to measure sort of the amount of heat exchange that's happening. So when we talk about the difference between temperature and thermal energy, for example, if we had a cup of, hot water or coffee at 70 degrees Celsius versus that of a bathtub at 40 degrees Celsius, once again, the bathtub will contain a lot more water molecules than obviously the cup of hot water or whatever it may be. So it's going to actually have a lot more stored thermal energy because of the motion of all those molecules and stuff. Although the coffee cup will have a higher temperature than the bath of water, and that's really because the amount of water that's in the coffee cup versus the amount of water that would be in a bathtub. It takes a lot less energy to heat up the little coffee cup of water, right? As it would if you took all that water that was in the bathtub and tried to heat it up on the stove. It's going to take a lot longer to change the temperature of it. Yeah. Was it the same question or a different question? Yeah, go ahead. It wouldn't, it really wouldn't. And again, because the temperature is really just a measure of what's going on. So it might make, we'll see a little bit more of this a little bit, or it might make a little bit more sense a little later when we talk about specific heat capacity. So for example, water has a specific heat capacity of something like 4.184 joules per gram per degree Celsius, which means you got to put in there about 4.184 joules of energy to see the temperature basically move 1 degree Celsius, right? So if you have a coffee cup, right, that maybe is only, let's say 50 grams, just randomly pick a number, but it's 50 grams, say, of water in there, right? It's not going to take as much energy as going to need it if you got like a bathtub that's got like 1,000 grams, which probably has more, but 1,000 grams, it obviously will take a lot more energy to see that temperature actually go up, right? So that's the idea behind the sort of the difference between those. We do use temperature as a measure of sort of what's happening with the energy, but it is also related to the volume of what you're trying to heat and stuff like that as to how big of a temperature change you would see. To relate this to like when people freak out, right, with the ocean temperature, it goes up by like a really small degree, right, of temperature, right? And maybe you think like, it's just like a small, like half a degree or something like that. Doesn't seem like a lot. But you think about the volume of water that's in the ocean, the amount of energy required just to move it that little bit of temperature, right, is an enormous amount of energy to do that because of the specific heat of water. So that's why in something like the coffee cup, we will see a much higher range of temperature because there's a lot less volume of water that you need to heat, and you'll be able to see that bigger temperature difference. Other questions? So heat is defined, as we've been talking about, as the flow of energy due to an energy difference. And heat flows from cold to hot, hot to cold. Which way does it go? Heat flows from hot to cold, right? Right. The hotter guy gets cooler, right? The cooler guy warms up, like you'll do probably this week in lab. You take some water, right, and you throw a hot piece of metal in there, right? The metal's temperature is going to drop because it's releasing all that energy right to the water. We'll see the water's temperature go up because it's absorbing all that energy. And we have our transfer of energy, like we've been talking about. The metal in that case would be exothermic, as it's releasing all that energy to the surroundings, which in this case would be the water that you threw it in. It's going to absorb all that energy, and we'll see a temperature change that will occur for that. So as we've been talking about, any process where we have basically that energy being released to the surroundings, or even really from the surroundings to the system, is an exothermic process. Again, lighting a Bunsen burner or anything with a flame, you could obviously put your hand near it, right? You can feel the heat coming off, being released from that combustion reaction that's occurring, as opposed to an endothermic reaction where heat and energy is absorbed. Like our ice cube example, if we take our ice cube out of the freezer and just put it in the out here in the room, it's going to pick up all the energy from the surroundings. That's because the ice cube is a colder temperature, right, than the surrounding air, which means it's going to move from the surrounding air hot to our colder temperature. The ice is going to pick up that energy and start to melt. Also, same thing happens when you take your liquid, right, water, throw it into the freezer to make ice cubes. When you put it in the freezer, the liquid water is actually warmer than the air in the freezer, right? So the energy from the liquid water and the heat is going to transfer out to the surroundings, and it's going to lose energy and eventually freeze back up as you kind of go in each way. And a reaction, right, if you're holding onto a test tube and you feel the test tube gets colder, right, that means the test tube's reaction is exothermic or endothermic. The reaction in the test tube is endothermic, right? Because the heat is going to come from your hand to the test tube as it absorbs it, right? That's why it feels cold to you. If you're holding on to a test tube and it gets really hot, that means the reaction inside is exothermic, right? All the energy is leaving the test tube into your hand that you're holding it, which is why sometimes we tell you don't hold on to the test tube, right? Put it in your test tube rack, because some are very exothermic reactions and it will kind of hurt as you hold on to it as it gives off that energy. Any questions on that? These are what are referred to as energy diagrams. And there's two types of energy diagrams that we're looking at here. We have an exothermic reaction and an endothermic reaction. So as we talked about a second ago, when we look at a reaction, which, you know, A reaction. Try that again. Reactants. The products. They kind of assume in chapter 10 that you did that chapter with the equations and reactions and stuff like that. So obviously, again, we have our reactants going to products, which is what happens in a chemical reaction. And we could look at the energy associated with it in each of these diagrams here. This would be our reactants right here, where they're starting in terms of energy. This would be our products, where they end up in terms of energy. And in this particular case, our reactants are higher in energy than our products. The only way for our reactants to get down there to the energy of the products is energy needs to be given off, which means it's an exothermic process in that case for those reactants to get down in terms of energy to the products. Earlier, we talked about delta H as a very common way that we express energy. And if you take the energy of the reactants and the energy of the products, and you take the difference there, that is how you calculate the enthalpy or change in enthalpy for this particular reaction. So if we look at the change in enthalpy, which is our products minus our reactants. In this particular case, if we look at where the energy of each of these guys are, the energy of our products is actually a lower number, right, than the energy of our reactants. So when we take the products, which is a smaller number, minus the reactants, which is a larger number, what type of number do you end up with when you take a smaller number minus a larger number? You end up with a negative number, right? So this is why the delta H value is negative in a reaction like this, because the difference between the energy of where the products end up at to where they started with is actually a negative change that occurs, and that implies that the energy is being given off. Any questions on that? Now, if we look at the guy on the right here, this is our reactants. This is our products. And once again here, we see in this case, though, that our reactants are actually lower energy than our products in this case. And that means in order for our reactants to get up to the products in terms of energy, energy has to be put in or absorbed for those guys basically to get up there to the products. And we also can take the difference between where the reactants and the products end up in energy. And if we do that, say down this way, delta H of our products minus the delta H of our reactants. Once again, here we can see that in this case, our reactants are a lower number than our products. So our products would be a larger number minus a smaller number. And that's going to give us a positive value for delta H when we take the difference between them. And that's why when we see delta H, it is referred to as being an endothermic reaction. And I would say that is very much the common way that exothermic and endothermic is displayed to you in chemistry. Is they'll give you an equation, and at the end of the equation, they'll go, the delta H value for this reaction is negative 300 joules or something like that, kilojoules. And just from the negative sign, you know it's exothermic, or if you have a delta H value that's positive, then you know it is a endothermic reaction. Any questions on that? Now, what happens as we go from reactants to products? Well, the only thing that happens is we pretty much break all the bonds here on our reactant side, and they basically reassemble on the product side as new things. So we make some bonds on our product side. And that's why, as you may know, when we balance an equation, what we start with and what we end with in terms of elements is always the same. We don't lose any elements along the way in a chemical reaction. And that's because bond making and breaking only involves electrons. So it has nothing to do with the nucleus, which is important for what element you're dealing with. So when we break bonds and make bonds, it's all about electrons, and they're basically just coming apart and reassembling. Now, in order for really a reaction to take place and for really products to be formed, there's actually two things that actually has to happen. there does have to be a collision between the reactant molecules, so they do need to collide. But not all collisions will actually end up in products being formed. When they hit each other, they do have to hit each other in the right location, kind of like the active side, if you will. And the second more important thing as well is they actually have to hit each other with the right amount of energy for that reaction to take place. So if something collides, two reactants collide, and they don't have the right amount of energy, or they don't have the right position, you will not get any products that will be formed. So what is sort of that minimum amount of energy? That is, if we look at our diagram here, as we head up the hill here to the top of the hill, between where the reactants started in energy and the top of this hill is what is known as the activation energy, and that is the minimum amount of energy needed for a reaction to take place. It is also sometimes referred to as E of A. So E of A, if you see that, refers to the activation energy. And that is really the minimum amount of energy is required for that reaction to take place, which means when those guys collide, if they don't have that amount of energy, you're not going to get any products to form. So they need an amount of energy to get there. The activation energy, as you can kind of see, is like the hill that the reactants has to climb to get to the other side. So it's the hill of energy that the reactants has to climb to get to their side. We could also look at it on our endothermic. So as we come up the hill here to the very top, that difference in energy between the reactants and the top of the hill is the activation energy there that it needs to climb to get to the other side. When we actually get to the top of the hill, which is the peak of energy in each of those diagrams there, this is what is sometimes referred to at the top of the hill as the transition state. And at the top of the hill, we have what is referred to as the transition state complex, or sometimes referred to as the activated complex. And that is something here, which is sometimes, for example, in a generic reaction, represented something like this. We'll have a little symbol type of thing at the top. And that is, as it is progressing up the hill from reactants to the top of the hill, what is happening is basically all those bonds that we have on the reactants are starting to break. And in the same sort of breath there, they're starting to kind of reassemble new bonds. So you have partially broken bonds as it goes up the hill in energy. You have partially made bonds as you go up that hill until you get to that transition state that's at the very top. Now, because the transition state and that transition state complex is at the very top of the hill, in chemistry, when we have something that's really high in energy, is that the state that things want to be in? Do they want to be high in energy or low in energy? Yeah, and much like us in life, right? We like to be in low energy, right? So pretty much everything that happens in chemistry is in an effort. A lot of it is to lower the overall energy that's sort of happening. So things in low energy is really more preferred than anything that's really high in energy. So this, as you can see from the graph, is basically the peak of energy that you could get to. It is as high as you go. So those transition state complexes are activated complexes. They are intermediates that have partially made bonds, partially broken bonds, and they really do not usually hang around for a very long time. And for a lot of years, you know, a lot of reactions, they're very hard if you wanted to try to isolate it, because they're not going to hang around a very long time. They're just going to kind of very quickly, when they get to the top of the hill, and a lot of reactions kind of drop down, you know, to the other side to make the products. So we have this kind of building up the hill in terms of energy, where we're breaking bonds, making bonds. We got this intermediate at the very top of energy, really unstable because it's the height of energy, where they're going to kind of quickly convert now to the proper bonds that they need to make the products as they drop back down the sort of hill of energy. Any questions on that? Yeah. That is, yeah, this delta H is the symbol for enthalpy, or to change in enthalpy. Yeah. Other questions? Now, when we look at the activation energy, it does actually play a good role in terms of how fast or slow a reaction will take place, and which again deals with the kinetics of the reaction. If I have a really big hill, right, versus a smaller hill for the activation energy, which one should go faster, the big hill or the small hill? Yeah, the one that has a lower activation energy hill, right? You would expect the reaction probably to proceed faster because there should be a lot more reactant molecules that have enough energy basically to get up and over the hill to the other side. So it's kind of like when you walk a hill, right? You got a real giant hill, right? It's going to take you a lot longer to get to the other side. Other people walking with you may look at the hill and go, no thanks, right? I don't have enough energy to go up and over that hill. So only maybe some people will get up and over the big giant hill. In terms of a smaller activation hill, right, there's probably a greater proportion of people, if you're walking with a bunch of people, they'll go, all right, I'll do it. It ain't that big of a hill, right? So we'll be able to kind of get up and over to the other side. So the activation energy hill plays a really big role in how fast or slow a reaction takes place. Typically, the bigger the hill, the slower the reaction versus something with a smaller hill. By the way, between the two, exothermic and endothermic, which one has the greater activation energy? The endothermic one on the right there. And that also makes sense based on overall that reaction is gaining energy, right? So that's going to help some guys have enough energy to kind of get up and over the hill to the other side. Any questions on that? Now, there is ways that you could kind of speed up a reaction. So let me just draw a generic sort of energy diagram that looks something maybe like this: reactants, products, energy. So in this particular one that I just drew, is this endothermic or exothermic? It is exo. Our reactants are higher in energy than our products, so this would represent an exothermic reaction. So a lot of times what we can do is add a catalyst to a reaction. And when we add a catalyst to the reaction, it is not a reactant. It is not a product. And it does not get used up in a reaction. Most of the time, the catalyst is there to speed up a reaction. Now, there are some negative catalysts that can be used to slow down a reaction, but probably 9 times out of 10, if somebody's talking to you about a catalyst, they're probably talking to you about speeding up a reaction. And a lot of times in equations where we see catalysts written, a lot of times they're up there on top of the arrow. So this is where we see a lot of catalysts listed. Maybe they write platinum or H plus for an acid, but something is kind of listed up on top of the arrow. Yeah. When you do delta H, it is. Yeah. Yeah. When you write the equation, it's always reactants going to products. But when we calculate something like energy difference, it's usually always products minus reactants, again, because that's like your final state minus your initial state. Other questions? So what happens with a catalyst is it actually finds a alternative pathway for that reaction to occur. And you could kind of think of it as finding a more efficient pathway for that reaction to occur. So for example, if we had a reaction that was like gas molecules flying around, so with no catalyst present, those gas molecules could be flying around, and they got to kind of wait until they come across each other, right, as they're flying around in order for a reaction to take place. So sometimes you can add a catalyst, like a metal catalyst, for example, piece of metal, where those gas molecules might be attracted towards the catalyst. And what that will now do is put everybody in a much closer location to one another. And that's going to allow the reaction to sort of take place a lot quicker than it would if they were just kind of flying around trying to find each other. So sometimes a catalyst works as simple as just kind of bringing everybody into a central location, which allows for a much efficient way for that reaction to take place. Ultimately, in terms of energy, what it does is, because it finds a more efficient or alternative pathway for that reaction to take place, what it actually does is, in this reaction here That would be my activation energy. When I would add a catalyst to this, it would actually lower the activation energy. So by finding that alternative pathway, what a catalyst is able to do is lower the activation energy. And that's important to the rate of reaction because now my hill is larger or smaller? Smaller, which means we're going to have more reactant molecules that have enough energy to get up and over to the other side. The result of that is going to be usually an increase in the rate of the reaction. So there are ways that you can sort of speed up a reaction that occurs really slowly. And as I mentioned before, when we talk about a reaction being spontaneous, it has nothing to do with how fast or slow it occurs. It just means that it can happen under those conditions. There's lots of spontaneous reactions which are super, super slow, like when you make ammonia, it's super slow if you don't put a catalyst in there. So by adding something like a catalyst, you can make a reaction that could take for all day kind of occur a lot quicker and a lot more efficient. Yeah. It's actually still there. So if it's a metal, it would still be there. If it's like an acid catalyst, the acid part of the H plus will still be floating around. So it's recoverable in a sense. It's still there at the end of the reaction. And that's why it's not considered a reactant or product, because there's no catalyst made as a result of it, and none of it's really used. It really is just there to sort of facilitate it. Like in your car, you have catalytic converters, yes? Or so you do, I guess, depending on what kind of car you drive these days. But catalytic converters, when you go to the smog check, they actually have catalyst in there. That's why they're called catalytic converters, because they have catalyst. That's why people steal it, because they have precious metals they're used for the catalysts that are in there. So as your stuff goes through there, the solid state sort of catalyst, so that doesn't really change unless it's really old and gets broken or anything like that. But that catalyst basically just stays there as everything sort of passes through it to sort of help the emissions. Other questions? Okay. So you do need to know energy diagrams. You need to know, the different parts of it. Delta H, activation energy, which one's an endothermic, exothermic. Any questions on any of that? So here's a couple other sort of energy like diagrams. This is our reactants. That's our products. So in this case, we see our reactants are higher in energy than our products. So it is exothermic, as the energy is going to be given off to the surroundings. And over here, decomposition of mercury 2 oxide, that's our reactants going to our products. So here are reactants, again, lower in energy than our products. Energy has to be put in or absorbed as we go through that reaction. Now, there are a couple other ways that, again, exothermic and endothermic is sort of displayed in a reaction. And sometimes they may actually just put a heat or energy value into the actual equation itself. So for example, here we have our combustion reaction, our methane, our CO2, and we have this, which is 213 kilocalories, which is a unit of heat or energy. And sometimes just generically they'll write heat or energy sort of into the equation. And if it's an exothermic reaction, we think of heat and energy as a product on the right-hand side of the arrow, like it's being given off and stuff like that. And in an endothermic reaction, we also can sometimes just see the heat or energy written into the equation. But again, here it's actually going to be on the reactant side. So we think of it as being a reactant. And it's like it's being absorbed or sort of gained, if you will, as the reaction goes forward. So if you see an equation written and they either put heat or energy on one side of the arrow versus the other, that will also tell you if it's exothermic or endothermic, or if they actually put a value, like here again, the kilocalories. But again, I would say probably 9 times out of 10, this is probably how you would see, sort of the energy displayed in an equation. You'll have your equation, you'll have your delta H value. By the way, that's negative what I got there, 155. That's endothermic or exothermic? It is exo, and really the number doesn't matter. It's just a negative sign. So that negative sign there is basically going to tell you that it's exothermic because of that. Exo. And obviously delta H, again, as we talked about, positive endothermic, delta H negative exothermic. That is why it's really important as you go do calculations involving energy in this class, future classes, that you should always keep the sign with your value that you get when you calculate energy, be it if it's positive or negative, because that tells people what type of reaction you're dealing with. Is it exothermic or endothermic sort of process going on? So sometimes people in these level classes are taught, don't worry about the sign, just get the number. But the sign is actually almost more important than the number in telling somebody what type of process is occurring. So whenever you calculate energy, always keep the sign. If it's positive, leave it positive. If it's negative, leave it negative. Don't just take the negative off. Any questions on that? And here's, again, a couple pictures from your book. As we were talking about, we're going to have some water that's separated by a barrier there in an insulated container, different temperatures. So we're going to flow from hot to cold in this case. Again, our cold water will pick up the heat and energy from the guy around it. We'll start getting these guys moving faster, and we will end up at some point in this insulated container. If you add them together, divided by 2, halfway between both temperatures is probably where they will sort of equal out. Again, our hot temperature gets colder, hot water, right? Cold water gets hotter. And as we were talking about, we use a lot of times wonderfully drawn thermometer to basically measure our temperature. So if we're measuring our temperature here, and we see that the temperature increases, is that water in my example losing energy or gaining energy if the temperature goes up? It is gaining energy, which means that we're observing in terms of the water here an endothermic process, right? Because our final temperature should be bigger than our lower temperature, our initial temperature. So this would be endothermic. When we do our change in temperature, our final minus our initial. If the temperature is going up, that means that's going to be a larger number. That's going to be a smaller number. And that's going to result in a positive value there for temperature, which in a lot of energy calculations is really the thing that determines sort of whether you get a negative or positive number for your energy value. Same thing if we took the water, put our thermometer in there, and we see the temperature decrease. That means that this is going to be a exothermic process. That means heat and energy is leaving the water, right? So we see it as a result, the temperature going down. And in this case, if we did our change in temperature, our final minus our initial, our final temperature is actually smaller than our initial temperature, which is larger. So once again here, if we take a small number minus a large number, we're going to end up with a negative number, and that is going to be what determines whether or not we have an exothermic. So a lot of times by simply just following the change in temperature, we can basically kind of determine, is that whatever we're measuring, wherever we got our thermometer in, is that absorbing energy or losing energy as a result of the temperature change that we see? Any questions on that? So that brings us to enthalpy, which is the change in enthalpy as we talked about. And the change in enthalpy, delta H, once again, is the most common sort of one that we look at in terms of energy. And as we've been talking about, basically the way that we calculate it is products minus reactants. And there is a couple of things that we need to do when we do this type of calculation. And that is usually the delta H values for your products and your reactants are found in tables. They're oftentimes referred to as delta H of formation, which is what the F stands for. And they're values for anything that you can look up in the back of a book and a table. When you do go to the table, it's really important that you look up what you need and the state. Is it solid, liquid, gas, aqueous? Sometimes people will just grab the first entry they see on the table, and it might be the right substance, but it's in the wrong state, and they'll have some different values. Things that are in their standard state, like H2, O2, a metal by itself, have values of 0 kilojoules per mole. So when we do a reaction, say like this, where we take something like 2A plus 3B goes to 4C. We could look up in our delta H table our values for A, say B, and C. And I'll just make up minus 10 kilojoules per mole. We'll do 20 kilojoules per mole. And we'll do negative 5 kilojoules per mole. Now, the per mole is important because when we look at the coefficients in a balanced equation, these are considered to be the moles of something. MOL for the abbreviation, MOLE for the whole word spelled out there. And when we do our products minus our reactants, we actually have to take the coefficients into account when we actually do the calculation. So in my made up example here, we would do delta H is equal to our delta H of our products minus the delta H of our reactants. And once again, we would go to the table, we would find our values in the appropriate spot, and we would do our calculation. So starting on the product side, I have a 4. So I do need to multiply 4 times the value of C, which in my made up example there is minus 5 kilojoules per mole. That 4 is really 4 moles, which takes care of the moles part of the calculation. That is all the products I have. Now I'm going to subtract that from my reactants. And I actually have 2 reactants here, so we got to take into account both of them. So this is going to be 2 times the value of A, which is minus 10 kilojoules per mole. And we're going to add it to our other reactant, which is 3 times 20 kilojoules per mole. And if we do all this here, we will end up with, I think, with minus 60, if I punched it in correctly here, kilojoules, which would be our delta H value for this particular reaction based on those numbers. This would be endothermic or exothermic. This will be exothermic as our value is negative. So it's important when you do this type of calculation that you actually do take into the coefficients on the equation into account for your calculation. And again, we're doing products minus reactants, final minus initial to give us the overall energy change that's happening in this reaction as it goes from reactants to products. Any questions on that there?